Gabriela, we can begin. Um, our talk is on complete colorings on circulant graphs and digraphs. Please.
Okay. Good afternoon. I don't know if it's. Let me see. I prefer that. But can you hear me?
I can hear you perfectly.
Yes. Yeah. Because. Okay. That's wonderful. First of all, thank you, Melvin and Kevin, to invite me to this conference. And I will talk about complete colorings on circulant graphs and digraphs. And well, I hope that you enjoyed the talk. And this is a joint work. Excuse me, I have one. I need I need something. Oh. It's a joint work with these three colleagues from Mexico, and Juan Jose Montellano, Mika Olsen, that she is from Denmark, but she used to live in Mexico, and Christian Rubio Montiel. And I hope that you enjoy the talk. And I don't know. Wow, I have a problem here. Okay. I start with the definitions. I have a graph, obviously, and I have a K coloring that, as usual, is a function in the vertices of the graph. But in this case, I am working with some specific kind of colorings that the name is complete colorings. And the idea of these colorings is that if you have two vertices with different colors, in fact, if you have two different colors, always there exists an edge that joins these two colors. For example, in this graph is a bipartite graph, you have a complete coloring here. Let me see here, because you also have between each pair of colors, you have an edge, yeah? And that is a complete coloring. You can see here that this coloration is not proper, but in this case, we don't have any problem with this, and we can have this kind of relation between two vertices with the same color. Okay, here, this coloring is proper also, but in this case, if I want to obtain a complete coloring, we want to maximize the number of colors that we want to use, or we can use. For example, if you have the complete graph, obviously you can use all the colors as vertices you have. And you have to maximize the number of colors depending of the graph, and the achromatic number denoted by alpha G is the maximum integer K, such that there exists a complete and also in this case a proper coloring. Okay. The achromatic number was introduced by Harari in 1967, and it's a natural upper bound of the chromatic number. Why? Because if you have a coloring that attains the chromatic number, it's also complete. Why? Because if that is not the case, you can recoloring the graph, and you can, if you have two colors that doesn't have an edge that join, you can recoloring the graph, and you obviously improve the chromatic number, and that is a contradiction. And then the colorings that attain the chromatic number are also proper, are also complete, excuse me. What happened on digraphs? On digraphs, we have exactly the same, but the concept of complete is you have now that if you have two colors, that it's necessary that you have an arc that goes from red to blue and another arc from blue to red, and that is the concept of complete. For example, in this graph, you have an arc that goes from red to purple and an arc that goes from purple to red. And also in this graph, you have exactly the same. And this digraph is coloring with three colors. And you always, if you can see the graph, you can always have this kind of arcs between any pair of colors. The diachromatic number is in this case, it's exactly the same, but in the graphs, that it's a maximum integer such that D has a complete and also a proper complete coloring here. Excuse me, we are on the graphs. And also we have another concept of another kind of colorings here. And we say that we have an I-cycle coloration of D if we have a coloration of the vertices where any chromatic class gives a non-cyclic graph. Okay, in this case, we have this triangle, but this triangle is non-cyclic because the name of this is a transitive tournament of size 3, and that it's non-cyclic, that it's not cyclic, obviously, because you have an edge, and obviously that it's not a cycle because you have only one vertex, and this is an acyclic coloration of this graph. Well, the dichromatic number was introduced by Neumann, and the idea here is that you are searching the minimum integer k such that any chromatic class are acyclic, and you are thinking in the minimum number here, okay? And this is a natural generalization for the graphs for the chromatic number, because if you have a non-proper coloring, and you have an edge in a graph, you can have not this edge, you can have two arcs or a digon, and you have a cycle of length 2 between these two vertices with the same color. And this is a natural generalization between chromatic number and dichromatic number for graphs. And clearly a coloring of that assign the dichromatic number is also complete, because in any case, the situation is that you don't have an edge between red and blue or blue and red, and you don't have a cycle between these two colors, and you can also recoloring and you improve the dichromatic number. And that's the idea, that you have a natural generalization. This is the dichromatic number, and you have here the minimum number. This is a transitive tournament. They don't have cycles here. You can use one color, and the dichromatic number is an upper bound, okay? And now we work with these two parameters, both in circulant graphs, okay? And the previous work is on cycles, because a cycle is a circulant graph, obviously, or we have a lot of work on related with the achromatic index in the projective, in the complete graph, and also the complete graph is a special case of a circulant graph. Okay, I will talk about the achromatic and diachromatic numbers, both in circulant graphs and digraphs. Okay. I want to recall what is a circulant graph. Obviously, I know that you know, but you have a set, and a circulant graph is defined as a graph with vertex sets equal to a group, and the edges are given by two pairs of elements of the group, if and only if the absolute value of these two is equal to a number that be in this set. Okay, let me to give an example that is a simple example. You have P5, P is 5, and here G is equal to 1, and you have a graph, because the difference between these two vertices is 1, and also this, and this, okay? And this is a graph. This is a circulant graph, and this is very trivial circular graph. Well, I use also another tool that is more related with number theory, and this is the concept of quadratic residue. Here, I construct two kinds of circulant graphs. If P is congruent with 1 module 4, I construct circulant graph, because in this case, if I have a quadratic residue and P is congruent with 1 module 4, the negative of this element is also a quadratic residue. And also we have another property. If I have two quadratic residue, the product is also a quadratic residue. And if I have a quadratic residue or a non-quadratic residue, the product is a non-quadratic residue. And here, the number of the quadratic residues here is the value of P minus 1 over 4. And moreover, if 2 is a non-quadratic residue, if and only if P is a prime of this type of primes. Okay. With this, I have a theorem, and if I have a non-quadratic residue and I live in this group, then I can bound the achromatic number of this circulant graph, and I can find a coloration with this number of colors. And then the achromatic number is greater than this number. And also, if I have specifically this prime, I have the quality in this case, okay? And in circulant graphs, I have some similar results, but here I use the other power of primes because I have another family of primes, and I define the circulant graphs. I have a set, I have also a group, and the arcs are giving with this definition, but in this case, we don't have the absolute value, and I have arcs, okay? And for example, this is a circulant digraph of over P equal to 7, and we have arcs with these weights. I say that it has these weights, or another people say color caylys or whatever, no? And I have the distance is 1, and here the distance is 2, and this is the circulant digraph with this example. Here, I use the properties of quadratic residues also, but in this case, the primes are congruent with 3 modulo 4, and here the situation is different. If I have a quadratic residue, the negative is not the quadratic residue. I have the double of the quadratic residues here, and moreover, also 2 is a non-quadratic residue if and only if P has these properties or has this characteristic. Okay, here I also have results related with digraphs, and I have some similar theorem. But what happened with the upper bounds? The upper bounds here is easy. It's really, really easy because it's, the upper bound is given by the number of edges that you have, and it is very easy to calculate that. And here, the upper bound is related with the number of edges that you have here, and that it's also easy to calculate because this value over 2, and this is smaller than the number of edges, and you make the arithmetic there, and you obtain the upper bound. That it's really easy. But this is our theorem, and this is a coloration, and I will give you a sketch of the proof, but really, 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 I will give you an example, because the sketch of the proof, it's a little complicated, and I prefer give you a nice example, but I will try to give a sketch. We will give a complete and proper coloring of this graph, okay, with this number of colors. And in fact, we have these colors because I take a complete graph of order 4q plus 1. And you have to note that each edge of this graph appears at least once. If you have a complete graph with this number of vertices and you enumerate all the vertices, obviously each pair of numbers appears in one edge and only in one. And we will construct a circulant graph using this complete graph, okay? I have this complete graph. This is a power of prime. This is a quadratic residues here. And we will give a circulant graph of this order with edges between vertices at distance 1 and a, okay? And we define a list of sequences as follows. The first sequences is given by the elements of the field or of the group in this case, and you start newly and you finish until a minus 2. In my example, a will be 2, and I am finishing with 0, but don't worry. After that, in this general proof, you continue with a minus 1, and in this sequence, you are between 1 and the next element. The difference is the next quadratic residue, that in this case is R2. Here you are jumping 1, 1, 1, 1, 1. In this, you jump between 1 and the other R2, 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 whatever. And R3, you start with the next of this, and you can see that Ri, you are jump here between this and this, you are Ri and whatever, okay? This is RQ, and the last sequence has only one vertex. And the concatenation of this contains all the edges, because any pair are given by a jump of one residue quadratic residue, or one non-quadratic residue. And you have here all the quadratic residues, and you have here all the non-quadratic residues, and you have all the difference between any pair of vertices here. And we don't have all, but we don't have some edges, but in the border, in the concatenation, we recover the numbers. And that is easy to see that we have a circular graph of order, because each Ri has this order and the last has order 1. In that case, we have a circular graph with this order because we are multiplying this by Q plus 1. And we have a nice coloring, okay? And now, exactly the same, well, this is the theorem, and I have here a specific, if A is equal to 2, we assign also the upper bound. And let me to show an example, because the example it's nice. You have 13 here, and this is the quadratic residues, or 13. You have 1, 3, and 4. And the sequences that we will be concatenation, that they are the following. R1 is 0, 1 until 12, and you repeat the 0. And you have this concatenation here. Next, you have R2, the next sequence start with 1, and you jump 3. That is the second quadratic residue. And you jump 3, 3, 3, 3, 3. And this goes to 1. And the first sequence, you are jumping 4, that is the next quadratic residue, and you jump 4, 4, 4, 4, 4, and you start with 4, and you finish here, and also you finish with 8, and you have the 0. And this is the concatenation. This is an example, and you have here all the jumps, because here you jump 1 with the residue, no, you jump 1 here, 3 here, 4 here, and with the next you jump 2, because it's 1 by 2, 3 by 2, and 4 by 2 in zeta 13. And you have all the jumps. And that is very nice, because we also assign the upper bound, and this is exactly the achromatic number of these circulant graphs. And in Circulant Digraphs, we make some similar, but I will jump because I want to introduce to the other topic that I want to show you. And this is the example. This is the circulant graph with this number of vertices, and I use exactly 11 colors, and this is the just bound. The bound is tight. And now I want to show you how can I coloring now the edges of a circulant graph. Okay, now I will be coloring the edges, and the idea is totally different. Okay, forget it, all the rest, or all the previous, forgetting the vertices, and now we have coloring the edges in the graph. And the upper bounds are given here by the number of edges that we have, and the upper bound is this. And it is not difficult to calculate that. And I will say some short here. If you have X is the smallest chromatic class, you have this number of edges over X, and you have one function, and here you have another function, and this function is calculating if you have the chromatic classes with the smallest number of vertices, and you calculate here how many another chromatic classes can touch the smaller. And with these two functions, as we have a decreasing function here and we have an increasing function here, we have the upper bound of this, and that is, we calculate, this is the calculation for the upper bound. Okay, and here the circulant graph is exactly the same. I am defining the circulant graph, that is the previous definition, but now I want to give you the tools that I will to use. I used to work with this kind of tools because I work a lot with finite geometry, especially I work with projective planes. And let me to recall you that a projective plane is a set of points and lines that satisfies the three properties. There exists one and only one line, between any pair of points. If you have two pair of points, you have only one line. Any pair of lines meet in exactly 1 point, and there exist 4 points in general position. That is 4 points that if you take 3 by 3, they are not collinear, okay? Fano is the smallest projective plane, and Fano has order 2. Each line has 3 points. By each point you have 3 lines, and the cycle is also a line, and you have exactly 7 points, 7 lines, and any pair of lines intersects, and any pair of points has a common line. And this is the smallest projective line that we have. Now, there exists a bijection between projective planes and complete graphs, and the bijection is very nice. Given a complete graph of order exactly the number, the order of the projective plane, we have a natural partition of the edges of the complete graph. Each line of the projective line induces a complete subgraph of the graph. And as any pair of the points induce a line, any edge of the complete graph lives only in one line or in one complete graph. Let me to show also an example. You have here Fano plane, and we will partition the edges of the K7 in triangles. Let me see. If you have this line, immediately in the complete graph, you have this triangle. The next line that you have is the line 174, and immediately you have this triangle. And the next line do you have is 165, and you have immediately this triangle. And as by any pair of points you have a line, but each edge be in exactly one triangle, and this is the partition. And the other magic thing is that any pair of triangles meet in 1 point, and that is the unique things that I will use to coloring the edges of the complete graph. Okay, these are the 2 properties that are needed, and that's all. Let me to show another example because it's very nice. You have K13, and you have the projective plane of order 4, and immediately you have K13, and for example, this line, the line D14, D3, D5, and D12 is this K4. Yeah, and for any pair of points live in a line, any edge be in a complete graph of of order 4, and any pair of lines intersects. Okay, any pair of these subgraphs intersects in 1 point. For example, I have here that is black. I have another, I don't remember exactly, but it's one of these pink lines, and I have another K4 that is one of these green lines. Okay, and I have a perfect partition. That is very nice. Well, I will introduce another ingredient here, that is the difference set. A difference set is a special set that there exists for some values, and if you have a field, there is a unique pair of different elements of the difference set, such that any element of the field is the difference of this. Therefore, if V is a difference set, then immediately the negative of the elements is also a difference set, and if you add something to the difference set, you obtain immediately a difference set. Something, obviously, an element of the group, nor something. Okay. This is the difference set, a difference set of zeta 7. This is a difference set of zeta 13. This is a different set of zeta 31, and wherever this is a different set of this. Okay. With this, we construct a specifically projective plan that we will use to coloring the circular graphs. You have this, and you have a cyclic projective plane of order Q, denoted with this notation, with this strange notation that I use for this talk. And you have a set of elements, and the lines are sets given by the different sets. Okay, let me show the example. That is very nice. This is a Cartesian representation of cyclic projective plane, and show you have 0, 1, and 3. And this is a different set because each of these, the edges are induced if you subtract these two elements, you obtain all the elements of zeta 7. For instance, you have 1 minus 0, you have 1, 3 minus 0, you have 3, 3 minus 1, you have 2. But if you rest 0 minus 1, you have minus 1, and minus 1 is 6 in zeta 7. And you have 5 here, and you have 4 here. You have all the elements of zeta 7, okay? And that's all. You have all the ingredients, because if you rotate here, you have this black. This is black. And if you rotate the black, you obtain the green. And if you rotate the green, you obtain the blue. And if you rotate the blue, you obtain the pink. And this is the projective plane. Yeah, this is the projective plane, and this is a partition of the K7. And that's all. This is the magic. Here you have K4, and you also have 1, 2, 3, 4, 6, and 5. You have all the elements here. And obviously, if you subtract 0 minus 1, you have the negative of 1. You have all the elements. And with this, you also rotate. And obviously, I can continue to rotate, but I don't have this. And I don't want that you remember this, because I want to finish. But I only show you what happened. Imagine if if T is the number of matchings that you have here. If T is equal to 3, I have this, but I can select the matching, and I can say, okay, I only want 2 matchings, or I only want 1 matching, and I have only the blue, no? And here, I can coloring the edges of the circulant graph, and this is very big, and I only show you with an example. Imagine that it's very nice. If T is equal to 2, you have the jumps 1, 2, 4, and 6. And you rotate, and you immediately coloring the circulant graph. Why? Why all the colors meet? Because this is a line, and this is a line coloring by matchings, and any color appears in all the vertices. And in a projective plane, any parallel lines intersects in a point. Then all the pair of colors intersect, and that is magic, I think. And this is exactly the same with the complete graph, and that was our first work in this topic. And this is the theorem, and obviously that is a magic, because we attain the upper bound, and we have the quality. We have the quality here, and this is a work that is just accepted. And thank you, that's all. Thank you for your attention.
Thank you very much. Are there any questions for Gabriela? I will.
Do you have any questions?
So again, if there are no questions, thank you very much. And
thank you so much.
And next talk will be in 3 minutes. So Kaylee, if you can share the screen, that'll be great. Put up your slides.